In this video, we'll be going through the 2022 Scholarship Physics exam. Okay, question 1, photons. Describe one difference in the use of the concept of quantization of energy between the photoelectric effect and the Bohr model of the atom. Okay, so the concept of quantization of energy just means that energy comes in discrete packets of energy. So the key difference between the photoelectric effect and the Bohr model of the atom is that they're referring to the quantization of energy of two different atoms, right? In the photoelectric effect, we're referring to photons, right? Whereas in the Bohr model for the atom, we're referring to electrons. So one of the key findings for the photoelectric effect is when we shine photons, right, that's a photon, onto a metal surface, we get electrons emitted from that surface. And it would seem that if we increase the energy of the photon, meaning we make it brighter, so we increase its amplitude, you would think that the electrons come off the metal surface with more energy, but that's not the case. Instead, the energy of the photon is related to its frequency, which is where we get E equals hf from. Okay, whereas with the Bohr model and electrons, we have a nucleus, and we have energy levels around this nucleus. And electrons can only exist on these discrete energy levels. And we can see this when we have our emission spectrum and our absorption spectrum of light. When these electrons are excited to a higher energy level and then spontaneously drop back down, they release a photon with an energy which is equal to the energy difference between these two energy levels. So the delta E of these two energy levels is equal to the energy of the photon. And what we get is, due to E equals hf, which we saw over here, we get photons emitted with discrete frequencies. And that's where we get our absorption and emission spectrum from, with discrete wavelengths of light on a screen. So putting this into words, in the photoelectric effect, the quantization of energy is used to describe how photons interact with matter, right? However, in the Bohr model, we see that the quantization of energy is used to describe the discrete energy levels of electrons within an atom. Okay, question 1b now. This question is fairly simple, pretty much a regular level 3 question. The key idea is to understand that this setup is essentially the same thing as having a string. So right now we're using light waves, but the waves on a string are effectively the same thing, same concept. And so we know we're dealing with standing waves. And so we have a mirror on this side and a mirror on this side. So when waves of light come this way, they hit the mirror and they go through a 180 degrees phase change and interact with itself upon its reflection. And so we get a standing wave. So the situation here is we're basically emitting light in our medium. So the idea is that we're going to be changing the wavelength of this light within this apparatus. And we're going to be changing it from 480 to 490 nanometers, right? And there's going to be standing waves formed within this cavity right here. But the problem with that is only certain wavelengths are able to form. So we have to figure out how many of those wavelengths are possible, which is what we're trying to find. How many standing wave modes are possible in this cavity? So we know the length of this apparatus doesn't change, so we can keep that as L. And you have nodes on each side. And when we have nodes on each side, we know that, we can draw this out right here. Only whole number of half wavelengths are allowable. We know that. So if the length of the cavity stays the same, we know that the next standing wave that's allowable will be 2 lambda over 2, and the next one will be 3 lambda over 2. So from this, we can form an equation. We can say that the length is equal to the number of modes times its wavelength over 2. And so we can rearrange this for n. Therefore, we get 2L over lambda is equal to. And now we have our wavelengths, which are 480 and 490. And we have our length, which is 5 centimeters or 0.05 meters, that's what we'll be using. So chucking our numbers in for wavelength is equal to 490 nanometers, we get 2 times 0.05 over 490 times 10 to the 9, because nanometers is, when converting nanometers to meters, we put it to the power of -9, and that's equal to 204,082. That's n, by the way, using this equation. And so for lambda is equal to 480 nanometers, we get n is equal to 2 times 0.05 over 480 times 10 to the -9, and that's equal to 208,333. Now, to find the number of modes that are possible between these two values, we can subtract the larger from the smaller, and so we get 208,333 minus 204,082, and we get 4251 allowable modes. There we go. Okay. The process of nuclear fusion in the sun releases energy which spreads through space in the form of electromagnetic radiation. The photons that make up this radiation carry momentum as well as energy, with the momentum per photon given by this equation here, where h is Planck's constant and lambda is the wavelength of the photon. The sun loses 4.3 times 10 to the 9 kgs of mass per second. Estimate the force exerted on the Earth by the photons it receives from the sun. Assume each photon has a wavelength of 550 nanometers, and every photon that reaches Earth is absorbed. First things first, we are given an equation, so we can, right off the bat, calculate the momentum of a single photon, which is using this equation here, and that's Planck's constant is 6.63 times 10 to the -34, all over our wavelength, which is 5.5 times 10 to the -7, and that gives us 1.21 times 10 to the -27 kgs meters per second. That is our momentum of one photon. Okay, now that we have the momentum of one photon using P is equal to mv, we can get the mass of the photon by rearranging this equation to m is P over v. So we have 1.21 times 10 to the -27 all over the velocity of a photon, which a photon is light. So it goes at the speed of light, which is 3 times 10 to the 8, and we get 4.02 times 10 to the -36 kgs. That is mass of a photon. Now, given that the sun loses 4.3 times 10 to 9 kgs of mass per second, we can get the total number of photons per second by dividing the total mass that the sun loses by the total mass of a single photon, and we get 1.07 times 10 to the 45. That's just total photons. Right, now that is the total number of photons that the sun releases per second. Now for this question, you need to realize that the sun releases photons in all directions. So it's releasing this many photons per second in all directions, right? This way, this way, this way, in all directions. So what we need to realize is we have our sun right here, but way over here we have our Earth, right? And let's get artistic in here. Let's go. And so over here we have our Earth. So the sun is releasing photons in all directions. And so what we need to find is this area that crosses with the Earth right there and comes out. If we imagine this in 3D, this is a sphere, right, of the sun's effective radius that is reaching the Earth. So the effective radius of this will be from here all the way to here. That is our radius of this sphere of emitted photons. And in order to get the surface area of a sphere is 4 pi r squared. So that's 4 pi, the radius of this radius that we mentioned here is the distance between the Earth and the Sun. And so that is way up here, and that is 1.5 times 10 to the 11. So we have 1.5 times 10 to the 11, and that is squared. And that is equal to 2.83 times 10 to the 23. That is the surface area of Sun's effective range. Right? And so what we now need to find is, now we have the surface area that the entirety of the Sun covers, we are only interested in this little bit here, the part where the Sun crosses with the Earth. We're interested in this portion right here. And so if you look at that from a frontal point of view, this is just the area of a circle. If you imagine we are looking from this point of view. And so the area of a circle is just pi r squared. And so we have pi, and our radius is the radius of the Earth, which is 6.37 times 10 to the 6, and that's squared, and that's equal to 1.27 times 10 to the 14 meters squared. And that's area facing Sun. And so we can get the proportion of the total number of photons absorbed by the Earth, and we can get that by taking the Earth's area that's facing the Sun and dividing it by the Sun's total surface area, and we get 4.51 times 10 to the negative 10 portion of total photons hitting Earth. Right? And so now we have the proportion of total photons hitting the Earth. We can times this proportion by the total number of photons emitted per second, which is this number right here. And that's equal to 4.82 times 10 to the 35. And that is total photons hitting Earth, right? And now that we have the total number of photons hitting Earth, we can times that by the momentum of one photon, which we calculated at the very beginning. And what that gives us is 5.84 times 10 to the 8. And this is momentum, as this is the total momentum of all photons hitting the Earth, because we have the total number of photons hitting the Earth, and times it met by the momentum of a single photon, we get the total momentum of all photons hitting the Earth. And as F is equal to delta P over T, we have our momentum, so 5.84 times 10 to the 8, all over T, which is, in this question, we're given per second. So this is all over 1 second. And so the answer is just 5.84 times 10 to the 8 newtons. And that's our final answer. For this next question, it relates to the question above, to comment on the significance of the size of the force exerted on the Earth by the photons. And so for this question, we can use our F is equal to ma, and we can rearrange it for acceleration. So if we take our force, which is 5.84 times 10 to the 8, and we put that all over the mass, which is the mass of the Earth, which is 5.98 times 10 to the 24, we get 9.76 times 10 to the 17, negative 17 meters per second. And if you imagine, that is a very, 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 very small number. And so, sorry, that is meters per second as well. That is a very small number, and so the force exerted is insignificant. We can put a comment under here and say, thus, force is in. Right, okay, if the Earth was covered by ice, it would be more reflective, and explain how this would affect your answer in part Part C. So if the Earth was covered in ice, the photons would reflect rather than be absorbed. So we can write that in as we see there. A key idea here is when we have our Earth, we can draw in another spectacular Earth. So we have our Earth, and when a photon comes along with a momentum, let's call this P initial, right? And because it is covered in ice, even though this Earth is not covered in ice, I forgot to add that, but pretend it is, the photon is reflected directly back, so we can call this P final. And we know that delta P, change in momentum, is equal to PF minus PI. Now, as momentum is a vector, it has direction. And so this PF is actually a negative because P initial is in the positive direction. So going right is positive and going this way is negative. So that means our delta P is actually negative PF minus PI. And so the delta P is actually negative 2P. Therefore, due to F is equal to the change in momentum over time, as delta P has 2x, therefore the force will also 2x. Right? The force will also double. And this is again assuming this is a perfectly reflective surface, which it probably wasn't. So at most it's 2 times the force, but it'll probably be in reality a lot less than that. Okay, that is the end of question 1. Okay, question 2. As measured by a stationary observer, the initial wind velocity is 10 meters per second from the north. The velocity of the water is 6 meters per second to northeast. And the final wind velocity is 10 meters per second towards southwest, in the opposite direction of the velocity of the water. By considering the wind direction before and after striking the sails, use impulse and momentum to explain how the wind produces a force on the sail. Okay, so as the wind has experienced a change in direction, therefore it must have experienced a change in momentum. Thus, due to F being the change in momentum over time, there is a force applied to the mass of air. Thus, due to Newton's third law, as every reaction has an equal and opposite reaction, there must be a force applied to the water. Explain how the wind produces a force on the water that has a component in the direction that the water is traveling. Okay, we can move this VWI vector over here. And so that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 boxes. So we can go 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. And we go up here. And we can redraw that as VWI like that. And so completing the vector, we get a vector coming there like this, and that is delta V. So therefore, due to Newton's third law, there is an equal and opposite reaction, so there is a vector of equal length, so that is 1, 2, 3, 4, 5, 6-ish. There we go, that's close enough. And so this vector right here is the change in velocity of the boat. So it's in opposite direction to the change in velocity of the wind. And so if we need to complete this vector, right, because this is the change in velocity of the boat, so therefore there must be a vector that causes that change in velocity. And so we can see that there is going to be a small, you can barely see that. Let's make that black. There's going to be a small vector right there. And that is the force in the direction that the rocket is traveling, and we can complete this right there. And so this is the small force that we are going to be talking about. The change in velocity of the wind is facing northwest. So if we have our compass right here, we have north, south, east, west. So that's that way, as you can see. Thus the force and change in momentum must also be in the northwest direction, as the force on the rocket is equal and opposite to the force on the wind. Goddamn, spelling mistakes. The force on the water must be southeast, so equal and opposite, southeast. even though this force is not in the direction of the waka that the waka is traveling in, there's a small component of this force, which is this guy right here, that is in the direction that the waka is traveling. Thus, there is a small forwards force pushing the waka forwards. Okay, so for this question, we are calculating the mass of the air that hits the sails each second. So what we are looking for in reality is mass per second. And this is where our dimensional analysis comes in very handy, because we know that mass per second is just kgs over s, or we can rewrite that as kg s to the minus 1. So we can write mass per second as just m, and that is our density times our area and times our velocity. The reason for this is because density is kg meters per meter cubed, area is meters cubed, and velocity is meters per second. As you can see, the masses cancel out, and we get kgs s to the 1. So that is why our dimensional analysis is very important, so we can construct these equations. So this is the equation that we'll be using. I'll rewrite it here. So we have our density, and we have our area, which is right there, and we also have our velocity. But the key idea here is that the wind is coming in at an angle, and so what we actually want is a component of that velocity. And so if we can take this out, and we can draw a perpendicular line right there, and we know that this line is 14.9 sine 28.4, as this is the opposite side and we have the hypotenuse. So that is our V, and so we can simply chuck this in as m is equal to our density, which is 1.23, times our area, which is 40, and times 14.9, if I'm correct. Yep. Sine 28.4 degrees. And we get 349 kgs. There we go. The sideways force of the wind on the sails causes the waka to tilt over sideways. In strong winds, the upwind side of the hull may lift out of the water altogether. Explain how the double hulled design of the waka helps it to stay upright in strong winds. Okay, so if we take an arbitrary center of mass, let's say our center of mass is just there, right? There's a force being exerted onto the sail, and this is at a distance from the center of mass. So there is a clockwise torque going that way. There is a weight force on this hull, and as it's in the water, there is an equal buoyancy force, Fb, going up. However, this hull also experiences the same weight force. However, as it is not in the water, there is no buoyancy force. So there is a net force going down. And so as this force is again at a distance from the center of mass, there is an anti-clockwise torque going down that way. Thus, as there are torques being produced in opposite directions, they cancel each other out, and that helps the waka stay upright. So we can write that down. Okay. The weight force of the left hull is no longer being supported by a buoyancy force, thus there is an unbalanced force at a distance from the center of mass. Thus there is an anti-clockwise torque being produced. This anti-clockwise torque opposes the clockwise torque produced by the wind, as the force from the wind acts at a distance from the center of mass also. Explain how the tilting of the waka will affect the force produced by the wind. Explain how the tilting of the waka will affect the force produced by the wind hitting the sails. Okay, so if we have our waka like this, and this is in the water, and we have a wind force coming in like this. If it were upright, there will be more of the sails exposed to the wind. So when it's tilted, the total area exposed to the wind is decreased. Thus, there's less wind striking the sails, and thus there is less force from the wind onto the sails. So as the waka tilts, there is less area exposed to the wind, thus the force from the wind is decreased. So for this question, there is a force being produced by the water flow, and so this force directly opposes the sideways force produced by the wind. If there's a force pointing this way, this will cause the waka to tilt this way. So the waka will want to rotate back this way, and so this angle right here will decrease, and so we can write that in. Okay. the sideways force from the water acts in a way that opposes the force from the wind that pushes the boat sideways, thus reducing the net sideways force. Thus, the angle between the waka velocity and the waka direction is reduced, causing the waka to travel closer in the direction that the waka is pointing. Now, there is a second part of this question. So if we, again, redraw our waka like this, and we have our hulls. Those are massive hulls, but we move. There is, again, our center of mass right here, and there's a force from the wind, thus producing a clockwise torque. Now, there is a sideways force being produced on this hull, and so that force acts in the opposite direction to the wind force. However, as you may see, this also produces a clockwise torque, and so those torques combine to produce an even larger clockwise torque, thus making the waka more susceptible to tipping over. So we can write that in also. Also, the sideways force from the water produces a torque in the same direction, which is clockwise, as the torque produced by the force from the wind. Thus, these torques add together, thus making the waka more likely to tip over. Alright, that is question 2 done. Okay, moving on to question 3 now. Okay, so for this question, we need to show that the constant velocity reached by the roller is equal to this equation right here, which is labeled equation 1. And so, as this roller moves through the magnetic field, due to Lenz's law, there's going to be a force that's actually pushing back against the roller's motion. So as the roller rolls down, it's going to be a force that pushes it back up. And it's the balance of these two forces that actually allows the roller to reach a constant velocity. When something reaches a constant velocity, there is no net force, because the net force will cause it to accelerate. And so the force that causes the roller to go downwards must be equal to the force that is pushing back up. And so that force that's pushing back up is actually Lenz's law. And so it's the balance between these two forces that allows it to go at a constant velocity. So the gravitational force down the slope is equal to mg sine theta. Now, the reason why this is mg sine theta is because it's down an inclined plane. If you don't know where this is derived from, I have a video of it on my channel, and so you can look at that to see where it's derived from. Now, if we use our right-hand rule, we can actually see there's a current being induced into this roller as it rolls down. We got our 3 fingers here, and we have the direction of the magnetic field, which is going directly up, and the roller is moving this way, so our thumb goes there, and our middle finger is coming into the page. So we know that I is here. And so we can calculate this current induced into the wire as voltage is equal to BV, which is velocity in this case, L. Now, one thing we need to realize is that in this situation, the roller is going down an incline. And so if we have our magnetic field and we have an incline like this, we're actually interested in this angle right here. We want the component of the velocity. This is because the velocity isn't perpendicular to the magnetic field, and so this is BVL cos theta. And the reason why this is cos theta is because if this angle is 0, so if theta is 0 degrees, then it's a max. But if theta was 90 degrees, then that's a minimum. So if we look at a cos graph, we can see here that at 90 degrees, the value is minimum, which is 0. But at 0 degrees, the value is a maximum. So from there, we can determine that this is a cos relationship rather than a sine relationship. So as V is equal to IR, that means subbing this in for this, we can get that IR is equal to BVL cos theta. And so our current is equal to BVL cos theta over R. And so as we said before, that the force due to Lenz's law is going to be BIL. And again, as this is not perpendicular to the magnetic field, so if we have, for example, B that's coming this way and we have an intersection, we can say that in this angle, we want the perpendicular angle between these two, and so that's a right angle, and this is theta. And so BIL sine theta is the relationship. However, in our case, we have our field lines. This is our B, and we have a line of L going down this way. We know that the force due to Lenz's law is greatest when it's perpendicular, so we can draw a perpendicular line like this. And this is our theta. However, the problem with this approach is that when we use sine is not in this equation, only cos is in this equation. So we need to find a relationship of BIL that uses cos rather than sine. So we can draw another perpendicular line right here. Right? And so this is also an angle. This angle right here is 90 minus theta. And so what we can see is sine 90 degrees minus theta is actually equal to cos theta. And we can also derive this as cos theta as well, because this is the adjacent and we have the hypotenuse. And so that is cos theta. And so that's how we get BIL cos theta. And if we want to prove this relationship right here, just quickly, we can see we have a cos graph and a sine graph. We can see that cos 30 is equal to 0.866025, and sine 60 minus theta, or in this case 30, is equal to 0.866025 as well. And so we can now sub in our current for this current in here, and we get FL is equal to BVL cos theta over R L cos theta. Expanding this out, we get B squared times velocity times L squared cos squared theta from here. And that's all over R. So again, as we said before, at constant velocities, the two forces are equal. So Fg is equal to Fl. So mg sine theta is equal to BV L squared cos squared theta over R. And so rearranging to get velocity, we get mgr sine theta all over, that's a squared, B squared L squared cos squared theta is equal to B. And so a little tree identity that we need to be familiar with is tan theta is equal to sine theta over cos theta. And so we can rewrite this equation as mgr sine theta all over B squared L squared cos theta. As you can see, we have tan theta right here. And so we get mgr tan theta all over V squared L squared cos theta is equal to D. And we get this expression. This expression right here. So if the magnetic field is in an opposite direction, then obviously B is opposite direction. Thus the induced EMF is opposite as well. And current is also opposite. And when I mean opposite, this is direction as well. So, because of these reasons, as Lenz's law opposes the current produced and opposes the change that caused that current to be reduced, which in this case is the slider coming down the slope. The slider will come down the slope regardless, right? Because the slider doesn't come down the slope because of its magnetic field. It comes down because of the force due to gravity, which is mg sine theta in this case. So as the slider is still coming down the slope, there is still a force due to Lenz's law coming up the slope. So there is still a force coming up the slope. opposing the slider. Therefore, there is no difference in the velocity of the slider. There we go. For small values of theta, so for small angles, the first equation that we derived before, it can be approximated as so. And so we just sub in these values to determine the accuracy of equation 2, which is this one, which is the approximation equation with the actual equation at 25 degrees or 0.436 radians. And so if we just write down what the original equation was, so E1 is equal to mgr tan theta all over b squared l squared cos theta. So as you can see, this section of the equation is actually the same as that question on the equation. And so we can just cancel those two out and not even consider them. So what we're actually comparing is tan theta over cos theta compared to theta plus 5 theta cubed over 6. And so for this, you have to use radians if you're comparing the two, because you can't use degrees in this equation right here. So we're going to use radians. So tan 0.436 all over cos 0.436. That is equal to 0.514. And so 0.436 for this equation. Plus 5 times 0.436 cubed all over 6, and that is equal to 0.505. In order to get the accuracy of the second equation, we can put the result from the second equation, 505 all over 0.541, and we get 0.98. So that means equation 2 is 98% accurate. For this next part C, we're just calculating the velocity. So we got our velocity equation. That's equation 1. So mgr tan theta all over b squared l squared cos theta. And we're subbing in these values here. Let me just move these down now. So to calculate the velocity, we just simply sum these values in. So we have a mass, which is 5.00 times 10 to the negative 3. G is 9.81, I believe. Yep. Tan 85 degrees all over B, which is 2 squared times 0.5 squared times cos 85 degrees. So putting that in the calculator, remember to change your calculator 2 degrees because we are working in degrees now. Made a slight error. Sorry about that. So we have times this by 10. I was wondering why it wasn't working. Tan 85 degrees. Okay. And so that's 64.3 meters per second. Now, for this, we have to use our own intuition to see if the equipment that we're using is suitable for this test. So we know that G in this case is equal to mg sine theta, and that is Fg, by the way. So if Fg is equal to mg sine theta, we know it's actually less than 9.81 because Fg is equal to mg sine theta, we know that the acceleration due to gravity is going to be less than 9.81 meters per second, because now we're actually not just directly using gravity itself, it's a component of gravity, it's the horizontal component. And so because the acceleration due to gravity is actually less than 9.81, we actually don't know the value, but it's less than that, we're going to need a huge apparatus or equipment to actually reach that constant speed. And so we can say it's not suitable. Okay, for last part of question 3, part D, explain whether the equation 1, which is V is mgr tan theta over b squared L squared cos theta is still valid if the roller rolls rather than just slides down the slope. So if rolling, we know that this means there's ek linear plus ek rotational. So we can see that in this equation, ek rot is actually not part of the equation at all, and so ek rot has no effect. Also, if you want to further confirm this, that the mg sine theta, ek rot has no effect, and also the back force due to Lenz's law, which was b squared v L squared cos squared all over r, ek rot also has no effect as well. So if the roller rolls, it has no effect on its velocity. So that means equation 1 still remains valid. So that will be it for question 3 now. Okay, moving on to question 4. The James Webb Telescope has a mass of 6.16 times 10 to the 3 kgs. It was launched on Christmas Day, blah, 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 and is now orbiting a point called L2, where it will remain in a direct line between the Sun and the Earth as shown in the right. Okay. State the period of orbit of the James Webb Telescope around the Sun. So because the James Webb Telescope remains behind Earth and directly in front of the Sun, so it's constantly following the Earth, it must have the same orbital period around the Sun as the Earth. And so the orbital period of the James Webb Telescope is exactly the same as the Earth's orbital period, which is 365.25 days. There we go. Calculate the net force on the James Webb Telescope at point L2. So the net force is going to equal to Fg of the Sun plus the Fg of the Earth. And so the Fg is equal to Gmm over r squared. And so F net is equal to the gravitational constant times the mass of the Sun times the mass of the James Webb Telescope, so mj, all over radius of the Sun squared. Not radius of the Sun, I mean our Sun, it's this distance here. Plus g, the mass of the Earth times the mass of the James Webb Telescope all over r e squared, and that distance re is this distance right here. So we can see some common terms. We have a g and mj on both equations. We can take that out for simplifying reasons. So we have g, mass of the James Webb Telescope, times mass of the Sun over rs squared plus mass of the Earth over re squared. And so just subbing in these equations, these values, we get gravitational constant, which is 6.67 times 10 to the negative 11. The mass of the James Webb Telescope is given right here. So that's 6.16 times 10 to the 3. And then we got the mass of the Sun, which is 1.99 times 10 to 30. And now Rs is this distance here plus this distance here. So we have 1.5 times 10 to the 11 plus 1.5 times 10 to the 9. That's all squared, plus the mass of the Earth is 5.89 times 10 to the 24 plus 1.50 times 10 to the 9 squared. And this is equal to 36.72 newtons. An approximation for two bodies in orbit around each other is that the period t on the orbit can be determined using the relationship using that equation there, where r is the distance between the center masses of the two objects, and m1 is the mass of the more massive body. One assumption of the relationship above is that m1 is much larger than m2. Explain why is it necessary to assume that m1 is much larger than m2. And so it's necessary to assume that m1 is much larger than m2, because if m1 is way bigger, way more massive, I should say, than m2, and so the center of mass of the entire system is approximately the center of mass of m1. And so that's why it's necessary to assume that m1 is much greater than m2, because if m1 were only slightly bigger than m2, then the center of mass might be somewhere here, and we need to calculate this distance and take that distance into consideration. State another key assumption of this relationship. This must be a closed system with no external forces, and so the only forces that are applied are gravitational. There we go. Okay, question 4c. In the case that m1 is not that much larger than m2, show that the period of orbit is given by this equation. Okay, so this is a proof equation, and so if we can draw out m1 and out m2, and if m1 is not that much large or massive than m2, then the center of mass will probably be around here, center of mass, right? And so both of these masses will be orbiting around a shared center of mass. So we can define this distance here as little r, and in the previous question, the distance between the two masses was big R, so we can leave that the same. Okay, so we know that the centripetal force will be provided by Fg. Fc is m2v2 over little r, because again it's going around the center of mass, and that is the radius of its circle. And that is equal to big G m1 m2 all over r squared. Now, in this case, it's r squared because the definition for this equation is the gravitational force is proportional to the product of the two masses divided by the distance between the center of masses of the two masses. So that is distance r right there. So we can get the value of r using this equation here, m1x1 plus m2x2 all over m1 plus m2. Okay, this is the center of mass equation, which is on your formula sheet. If we take m2 as the reference point, that means x2 will equal to 0. So we can just get rid of this. And so r is equal to m1 r, big R, over m1 plus m2. Now, x1 turned into big R, because if we're taking m2 as a reference point, then this distance here will be x1, which is just equal to r. Now, so far, out of all the equations that we've formed, there is no period, there's no t. So we need to figure out a way to incorporate this into our equation. We know that velocity is distance over time. If we apply this equation to a circular path, then we get v is equal to 2 pi r, because the circumference of a circle is equal to 2 pi r, and that is all over the period. So that means that v squared is equal to 4 pi squared r squared, all over t squared. Subbing our velocity into this equation, we get m2 pi squared r squared t squared, all over radius, and then g m1 m2 all over r squared. This can be further simplified to m2 4 pi squared r over t squared, and that's equal to g m1 m2 all over r squared, big R squared. Now, in our equation, we want t to be at the top of the fraction, so we can take the reciprocal to invert the fractions. So we get t squared is equal to m2 4 pi squared r is equal to r squared, gm1, m2. Now that we have m2 on both sides and it's both on the bottom, we can cancel these out. So we get t squared is equal to 4 pi squared r is equal to r squared gm1. Now chucking this lot onto this side by multiplying by 4 pi squared r, we get t squared is equal to r squared 4 pi squared r over gm1. Now we can sub in our r equation into here, and we get t squared is equal to r squared 4 pi m1 r over m1 plus m2 all over gm1. Now we can cancel out these two m1s as they're both on the top and bottom, and we get t squared is equal to r squared 4 pi squared r all over gm1 plus m2. Now this can be simplified by taking the like terms of both r's, and we finally get t squared is equal to r cubed 4 pi squared all over gm1 plus m2. And that is our final equation. Okay, for this question, we need to realize that as the Earth, moves through this distance here, which we can label that angle theta, it will complete a full rotation plus an extra little bit, so the moon will be here, and that angle is also theta. These angles are the same. So in saying that, we can say that the distance covered by the moon, which we measure in radians, is equal to a full rotation, which is 2 pi, plus that angle that the Earth moves, which we can call theta e. Now we know that theta is angular velocity times time, so we can say that the angular velocity of the moon times time is equal to 2 pi plus angular velocity of the Earth times time. Collecting like terms by moving this on the other side, we get Wmt minus omega et is equal to 2 pi. Taking out t as a like term, we can get t Wm minus We is equal to 2 pi. Then dividing both sides by omega m minus omega e, we get t is equal to 2 pi all over omega m minus omega e. Now we know that omega is equal to 2 pi over t, where t is our period, so we can solve that in, getting t is equal to 2 pi all over omega m is equal to 2 pi over the period of the moon, which is 27.3 days. So we get 2 pi all over 27.3 minus, again, 2 pi. So the angular velocity of the Earth is equal to 2 pi all over TE. And that is, up here, should be 365.25 days. Now we can take 2 pi as a common factor between these two, so we get 2 pi is equal to 2 pi 1 over 27.3 minus 1 over 365.25. And then as there's 2 pi on the top and bottom, we can cancel that out, and we get t is equal to 1 all over 1 over 27.3 minus 1 over 365.25. And that is equal to 29.5 days. There we go.